I'm going to show you a couple of examples of different proofs for A and B, and then we're going to talk about the non-permissible values, the part I, in this right after that. So first of all, the first proof, A. Here is a great example. This person decided to change everything to sine and cos at the beginning. So they changed cotangent to cos over sine. They changed cosecant to 1 over sine. And then they had a fraction over a fraction, so they multiplied by the reciprocal. The sine values canceled out, and they left with just cos. So, perfect, full marks, great. I'm going to show you two more examples of part A that have small little mistakes. And you have to see if you can find those little mistakes. Okay? So you notice how this one, cos is equal to cos. Here's our first one. In the end, they get cos equals cos. So if you just look at the end, it looks like everything's fine. What happened?
They forgot to do 1 over sine.
Okay. So Peter, what did you say? Where did they make a mistake?
The first mistake, they forgot to do 1 over sine.
So here they changed cosecant to sine, but they didn't write 1 over sine. You notice that? And then, when they multiplied by the reciprocal, they didn't really do the reciprocal. Because if this was sine theta over 1, then when you multiply by the reciprocal, you should have written 1 over sine. So they undid their mistake by making another mistake, and everything worked out. Sometimes you got to be careful of this, because you know you want this to work, so you just make something work right above it, and hopefully that in the middle, if you make it blurry enough, maybe the teacher won't notice. No, it doesn't work. I will notice. So don't make, if something's going wrong, don't start inventing things to make it appear right in the end. You end up losing more marks that way rather than just going, okay, it's not working, and just leave it at that point. Because this person had a mistake here, which would be one mistake, and then they made a second mistake, so there would be 2 deductions instead of 1, even though they made it work in the end. Now, as far as I'm going to go back to the nice one here, and we're going to talk about non-permissible values. Now, non-permissible value is when something's not possible. And one of the things that we know from math is you're not allowed to divide by 0. In fact, the only thing that we have in proofs is dividing. There's no square roots of negatives. So we're going to look, where are all the places that we divide in this question? So while we were doing our proof, while we're dividing at the beginning, and then once we change cotangent to cos over sine, that means we're dividing by sine here, we're dividing by sine there. We're dividing by sine in a lot of places. Even though in the end it all simplifies out to nothing, when you look through your proof, there's a number of places where you're dividing. So what you have to do is you have to think about cosecant of theta can never equal 0, and sine of theta can never equal 0. Where does that happen? If we can figure out where they equal 0, then we can list all of our non-permissible values. So we're going to start with the easy one, which is sine of theta. Okay? Is sine of theta ever equal to 0?
Yes.
Yes. If you solve it between 0 and 2 pi, it's at 0, pi, and 2 pi. So if you wanted to write all of the zeros, and we did this at the beginning of chapter 6. We wrote down all of the zeros, and it was really complicated. Now, if you think about the general solution, it becomes a little bit easier. Because what did we do for our general solution? We got our answers, and then we could add 2k pi to all of those. And then it would list all of the non-permissible values. So theta can't equal these ones. A short way to write all of these is theta couldn't equal k pi, where k is an integer. It's not wrong. If you wanted to list all 3 of those and go plus 2k pi for all 3 of those, that would be fine. But this one in particular, I think you can see that it's like 0 pi, 1 pi, 2 pi, 3 pi, 4 pi. 0 plus k pi would be fine as well. So this would be all of the ones where sine of theta can't equal 0. Now, if cosecant of theta can't equal 0, because that's a place that you're dividing, well, that's like saying 1 over sine of theta can't equal 0. And I have a question for you about fractions. When are fractions equal to 0? Can you give me numbers? Give me some number on the top of the fraction, number on the bottom of the fraction, so that it's equal to 0. 0 divided by 2. Perfect. Is there any other ones, or is that the only one?
0 divided by anything.
0 divided by anything. So 0 divided by 7. 0 divided by 351.8 is equal to 0. But the important thing is, if I make it 1 over something, can I put something on the bottom that would make it 0? No. Some people are tempted, right? You're tempted to put a 0 on the bottom, but that doesn't work. That's not allowed. Now, the reason I'm showing you this is, it seems really obvious, but a fraction is only equal to 0 when the numerator is equal to 0. So if we take that back to our complicated thing that we were trying to figure out, 1 over sine theta, when is that equal to 0? Never. So you don't have to worry about that one. Cosecant is never equal to 0. So the only non-permissible values in this one are that theta can't equal k pi. Let's look at our second proof. Our second proof here was cos of theta is 1 plus cos of theta, or 1 plus secant of theta. I have a nice proof here done by someone. What I like about this question is that it really stresses the main strategy that we've developed so far. If you can change things to sine and cos and get a single fraction on both sides, almost every time so far you can prove your identity. So in this one, change the secant to 1 over cos. Well, now I have fractions inside of fractions. I want to get a single fraction on the top and a single fraction on the bottom. So on the bottom, they put things together to get 1 plus cos theta over cos theta. And what I like about this question is that sometimes the top throws people off, because they're like, it's 2 things. Yes, it's 2 things, but you could write it as a single fraction all over 1. Does that make sense? That 1 plus cos theta, which is on the top, is the same as 1 plus cos theta over 1. And so then you do have a single fraction on the top, a single fraction on the bottom. You can multiply by the reciprocal. The 1 plus cos thetas cancel out, and boom. Your left side is equal to your right side. So again, here's your main dividing line. I'll make it in. You work until you get a single fraction on the top and a single fraction on the bottom, and then you can multiply by the reciprocal. For this one, our non-permissible values, when are we dividing? Okay, here we're dividing by 1 plus secant theta. Here we're dividing by cos. Here we're dividing by cos, we're dividing by cos, we're dividing by cos, and then here we're dividing by 1 plus cos. So we need to look at all of those to figure out our non-permissible values. So we'll start with the easiest one. We'll say if cos of theta can't equal 0, when does that happen? When is cos of theta 0? Pi over 2 and 3 pi over 2. So you can write the general solution, and again, you can write these separate, or in this case, you could combine them, but I'm just going to add 2k pi to each of them. Those would be the non-permissible values for cos. That is one of them. When looking at these ones and deciding which one I'm going to do next, I think 1 plus cos theta is easier than 1 plus secant theta. So we'll start with that. For the second one, if 1 plus cos theta can't equal 0, what does that mean? That means that cos cannot equal -1. When does that happen on our unit circle? At pi. So if you wanted to write the general solution, add 2k pi. Since there's only one answer, we can do that right away. And so that would be another set of non-permissible values in this question. And the last thing that we've circled where there's dividing is 1 plus secant theta. If 1 plus secant theta can't equal 0, well, that's the same as 1 plus 1 over cos of theta not equaling 0. How do you deal with that fraction? Well, we can work with this. Here, I should erase that. How do I get rid of a fraction? What would I have to do to get rid of that cos on the bottom? Multiply by cos. So if I multiply both sides by cos, which would multiply this by cos, and this by cos, can you see that you would get cos of theta plus, and cos over cos would just simplify to 1, can't equal 0. And do you notice that that's the same as what we solved before? So we're done. We could continue solving it, but since we've already done that, our non-permissible values for this part B are all of these ones plus those ones. Usually on the exam, they don't ask for all the non-permissible values where you have to do the general solution. Sometimes they just ask for, can you give one non-permissible value? But if you do have to list them all, and it has come up a couple of times, then it's just like a general solution question. You find out from 0 to 2 pi, what are your non-permissible values, and then add 2k pi to all of them. For this, not that one, for this second proof, before we get to example 3, again, the method that you saw in that one example was perfect because it really practices, can you get a single fraction on a side? Can you change things to sine and cos? That is the number one strategy that's going to help you in this unit for proving identities. As we get into more complicated ones, and this morning we're going to take some time to start working on some more of the more complicated proofs on that sheet that we had, we're going to start to learn some new strategies. So I'm going to introduce to you sort of two new strategies that are sort of combined into one for this one. So we're going to prove this one. And one of the strategies that's going to come up is multiplying by 1. Now that doesn't seem like that's too complicated. You probably are pretty good at your 1 times table. You probably know it up to at least like 12 or 13, maybe even higher.
I don't know up to a billion.
Oh, wow. Okay. So why is multiplying by 1 so important? Well, when you multiply by 1, you can change what something looks like without changing its value. For example, 3/8 is equal to, well, if I multiply both things by 7, 21 over 56. What have I done when I multiplied by those 7s? I've multiplied by 1, because 7 over 7 is equal to 1, but I've changed what my answer looks like. So we're going to use a strategy of multiplying by 1 in our identities, but what number of 1 that we're going to use is going to change. And this is where I've got another strategy here that I've named it myself. I call it the build the other side strategy. So when looking at this proof, can you see on the right-hand side there's a 1 plus secant on the bottom of that fraction? So if I wanted a 1 plus secant on the left-hand side on the bottom, I need to put it there. So I'm going to write cos of theta And then I'm going to say, oh, I want a 1, because it's cosine theta over 1. I want a 1 plus secant theta on the bottom. If I did that, then at least the bottoms would be the same on my left side and my right side. But I can't just multiply by 1 plus secant theta. But if I multiply the bottom by 1 plus secant theta and the top by 1 plus secant theta, then I'm multiplying by 1. And my strategy here is to try to build the other side so something is the same. Well, this will make the bottoms the same. And what happens on the top? Well, if you distribute this cos times 1 is cos of theta. Cos times secant theta is 1. Oh, we're done. Proof is done. One step. So sometimes the build the other side and multiplying by 1 can make the proof even shorter. And sometimes it's going to be really helpful to see that strategy as we get into the more difficult ones.